we can look at functions of more than two variables. Remember, in a function that had one independent variable, we wrote as y equal to f of x, or the implicit form was a function of x and y equal to 0. That was actually a graph that was in the xy plane. If you had two independent variables, this is just what we've been covering in this section so far, z would be a function of x and y in the explicit form, and the implicit form would be a function of x, y, and z equal to 0. So the equation would have x's and y's and z's, and that graph is a surface in the xyz plane, or the xyz coordinate system, xyz space. If you had three independent variables, then your function would be of the form w equal to f of x, y, z, or implicitly it would be some expression with w's, x's, y's, and z's, but the graph would have to be points x, y, z, w, so that your graph would have to reside in R4, which about the best we can do visually is putting a graph in R3. That's what we're used to with conventional methods. So if you want to visualize something in R4, there are other ways to try to do that. So the function given explicitly by y equal f of x1, x2 up to xn gives a unique real number y to each point that's in the set D, which is the domain in Rn. So the number of independent variables here is denoting the size of the space. So the number of independent variables, if it's n, means the subset, the domain is in Rn. The range is just the set of all real numbers. So it's just the values that the y here has. And so if you were graphing it, then you would have x1, x2 up to xn, comma y, and that would be graphed in R of n plus 1, the n plus 1 space. So let's find the domain of these functions. The same ideas. You're looking for what values of x, y, z. Because we have three independent variables, the domain is going to be a subset of 3 space, R3. So the domain will be the set of all x points, x, y, z, so that this will exist. So that means that 16 minus x squared minus y squared minus z squared must be greater than or equal to 0. So that's the same thing as saying x squared plus y squared plus z squared is less than or equal to 16, which is everything inside a sphere of radius 4. So remember, the center is at 0, 0, 0, and the radius of this sphere is the square root of this left side. So the domain then is the set of all points in R3, x, y, z, such that you could just say x squared plus y squared plus z squared is less than or equal to 16. But that is, if you want to picture it geometrically, that's everything on or inside of a ball of radius 4 with the center at 0, 0, 0. Now, the domain of the second one, when you have a rational type expression like this, you have to make sure the denominator is not 0. So I know what the domain is, what it appears to be, because they're telling me here that it has 3 independent variables. So the domain will be the set of all x, y, z. Even though I don't see an x in the right side, I can tell it's one of the independent variables, such that z minus y is not 0. So that means z is not equal to y. Okay, so that's all the points in 3 space, so that y is not z, which means that y minus z is not 0, which we're talking about all the points in R3 that are not on that plane, y equal to z. Okay, now one way to visualize these when you have more than the 2 independent variables, since the graph of this would actually be in R4, is to look at what's called level surfaces. So instead of looking at the fourth dimension, you're looking at constant values for the W and finding out what would those values. So what you're doing is you're finding all the points, everything on like one of these paraboloids would have a constant value of W. Okay, so now let's see if we can look at the level surfaces. I'm going to look at just specific values of W. So W equal to 0 would be 0 equal the square root of z minus x squared minus 2y squared, which is equivalent to z minus x squared minus 2y squared equal to 0. Or just z equal x squared plus 2y squared. Now, I can see that's a paraboloid. If you notice that if x is 0, you have a parabola. If y is 0, you have a parabola. So that's giving you the yz and the xz traces, which would be parabolas. And if z was equal to 0, we would have a single point down here, which would be 0, 0, 0. So, and the traces, if you let z be positive values, this would just be ellipses. So we've got an elliptical paraboloid when the W value is 0. So this paraboloid here, the one going down to the origin, occurs when W is equal to 0. So that whole paraboloid is a level surface. That one, all the points on that paraboloid will actually have a W value of 0. So now let's look at W equal to 1. We would have 1 equal to this, which would mean that 1 equal to z minus x squared minus 2y squared. So z equal to x squared plus 2y squared equal to plus 1. Again, you've got a paraboloid, but now it's shifted up 1. And so that would be this paraboloid. And every point on that paraboloid corresponds to w being 1. W equal to 2. Let's just go ahead and go to 3. So that is z equal x squared plus 2y squared plus 9. And so that would be this paraboloid right here. Every point on that paraboloid plugged in, that points x, y, z that are on the surface of that paraboloid, every point on that paraboloid would correspond to a value for W of 3. So that's a way to not have to worry about a fourth dimension. So you're actually looking at constant values of the W and looking at that whole surface that would map to those constant values of W. Okay, another way that there's a graph in the book for this is to use points in R3 and then to use colors, representing some fourth value. So an example that the book gives you is having all the points in the heart and having that fourth value actually be maybe the electrical activity of the heart, and it might be denoted with a color. So it might have colors representing that fourth value, whatever the W is, and they might be some certain ranges of electrical activity. But you might look at those pictures, but it's giving you another way to visualize these curves or these equations in R4, since we really can't graph 4 dimensions well. So we'll use something to represent the fourth one and look at those points in R3 having those values.